Okay, so it's more or less this time. So I'm the chair today. Okay, great. So, well, we're very pleased to have Yunhe Sheng from Jing University. He will talk about deformations, cohomologies, and homotopy developed in Rota-Baxter Lie algebras. Thank you, Sheng. And I'm going to share the slide for people because there are many formulas. So, you can go ahead.
Okay. So, yeah, thank Chen Chang for the introduction. And first, I would like to thank the organizers for the invitation. It is my great honor to give a talk on this global Poisson webinar. So the title of the talk is Deformations, Cohomologies, and Homotopy of Relative Rota-Baxter Lie algebras. And this is a joint work with Chengming Bai, Li Guo, Andrei Lazarev, and Rong Tang. The notion of Rota-Baxter operators on Lie algebras was introduced as the operator form of the classical Yang Baxter equation. So a linear map T from G to G on a Lie algebra G is called a Rota-Baxter operator of weight lambda if the following condition is satisfied. So here there's a lambda, and the Smirnov-Sansky proves that if there is an invariant, non-degenerate, symmetric bilinear form on G, then a Rota-Baxter operator and a triangular R matrix are equivalent. So in this talk, I will mainly consider Rota-Baxter operators of weight 0, but before that, I give two examples of Rota-Baxter operators of weight 1. So let the Lie algebra G be the direct sum of two subalgebras, say G1 and G2. Then we define T from G to G by the following formula. So T of x1, x2 equals to the minus of x1. Then it's straightforward to deduce that T is a Rota-Baxter operator of weight 1. There is a close connection between Rota-Baxter operators of weight 1 and the solutions of the modified Yang Baxter equations. So let R be a solution of the modified Yang Baxter equation. That is, R satisfies this equation. Then under the transformation, R equals to the identity plus 2 times T. The operator R satisfies the modified Yang Baxter equation if and only if the operator T is a Rota-Baxter operator of weight 1. Yeah. Then Kupperschmidt introduced the notion of a relative Rota-Baxter operator, which is also called an O operator on a Lie algebra G. On a Lie algebra G with respect to arbitrary representation. So a relative Rota-Baxter operator on a Lie algebra G with respect to a representation V rho is a linear map T from V to G, satisfying the following quadratic condition. And a relative Rota-Baxter Lie algebra is a triple.
Sorry, I think someone's mic is not muted, and that's why we have those sounds. Could you, everybody besides the speaker, mute your mics? Or, yeah, okay, thank you.
Okay, thank you very much. Okay, so a relative Rota-Baxter Lie algebra is a triple where G is a Lie algebra and rho is a representation of G on the vector space V, and T from V to G is a relative Rota-Baxter operator. So in the SQL, when we say a relative Rota-Baxter operator, we will only mean the operator T. But when we say relative Rota-Baxter Lie algebra, we will mean the triple, which consists of Lie algebra representation and the relative Rota-Baxter operator. Okay, so now we give the graph characterization of relative Rota-Baxter operators. So we consider the semi-direct product Lie algebra structures on the direct sum of G and V. Here is the formula of the semi-direct product Lie algebra structure. And then a linear map T from V to G is a relative Rota-Baxter operator if and only if the graph of T, which is defined by this formula, if and only if the graph of T is a subalgebra of the semi-direct product Lie algebra. So this implies that a relative Rota-Baxter operator gives rise to a complement of the Lie algebra G in the semi-direct product Lie algebra. Now I give some examples. Yeah, let R in vector 2G be a triangular R matrix, and then we define R sharp from G star to G by this formula. Then it turns out that R sharp is a relative Rota-Baxter operator on G with respect to the coadjoint representation. And it is well known that a triangular R matrix gives rise to a triangular Lie bialgebra, and which we will denote it by GR. And we will see in the sequel that deformations and cohomologies of triangular Lie bialgebras can be studied using the general framework of relative Rota-Baxter Lie algebras. Okay. So let me give another example. Let omega in vector 2 G star be a simplices structure on a Lie algebra G. Then the inverse of omega sharp is a relative Rota-Baxter operator on the Lie algebra G with respect to the coadjoint representation. Here, omega sharp is from G to G star defined by this formula. Okay. So besides other applications of relative Rota-Baxter operators, I would like to mention the following.
You know the R matrix is that is weight 1 or weight 0?
Weight 0. Weight 0. So in the sequel, we will only consider weight 0 case.
Right. Weight 0 will really be the solution of Yang Baxter equation, right?
Yeah. And for the weight 1 case, it corresponds to a modified Yang Baxter equation.
Okay.
Yeah, but in this talk, we will only consider weight 0 case, which corresponds to the triangular R matrix.
Like another way to describe a solution of Yang Baxter equation.
Yeah.
Okay, great.
Yeah.
Okay. Perhaps I also have a question. So you explained that this Rota-Baxter equation is related to other structures, but how is it? What's the logic of the game? Is it easier to find some other structure and then from that obtain a solution, or is it easier to solve Rota-Baxter equation and then from that construct those structures? Like what I want to ask, is any of it easy, or is it all equally complicated, or like kind of what's the logic of the game?
Yeah. So for the triangular R matrix, so the triangular, so the classical Yang Baxter equation is a tensor equation. Namely, R is here as is in vector 2G, so it is a tensor, and we need to consider the tensor equation. For example, R equal to 0. But if we consider the relative Rota-Baxter operator, and it is a linear map, so the equation becomes the equation of linear maps. So somehow they are equivalent, yeah. But if we view such tensor as linear maps, sometimes we have some advantages.
Okay, thank you.
Okay, thank you. Yeah. So here I would like to mention some algebraic application of relative Rota-Baxter operators. Here are nine algebras. In the middle, it is commutative algebra, associative algebra, and Lie algebras. And actually, relative Rota-Baxter operators correspond to splitting of algebras. So more precisely, if we have a relative Rota-Baxter operator on a Lie algebra, then we can obtain a pre-Lie algebra. And if we have a relative Rota-Baxter operator on an associative algebra, then we can obtain a dendriform algebra. Yeah. So on the other side, we have similar operators, which are called averaging operators. And averaging operators will give rise to duplication of algebras. Yeah. Okay. So so our purpose is to study deformations, cohomologies, and homotopy of Rota-Baxter Lie algebras. And our approach is to use the controlling algebra. So more precisely, we construct an L-infinity algebra whose Maurer Cartan elements are relative Rota-Baxter Lie algebras. So we will call this L-infinity algebra the controlling algebra. Okay, so as soon as we have this controlling algebra, a relative Rota-Baxter Lie algebra gives rise to a twisted L-infinity algebra that controls its deformation. And then the L1 in the above twisted L-infinity algebra will define a cohomology of the relative Rota-Baxter Lie algebra. And finally, if we replace vector spaces by graded vector spaces, and then we can get homotopy relative Rota-Baxter Lie algebras. Okay. Yes. So these are what I want to do. And first, I gave an example of the controlling algebra for Lie algebras. Okay. So now let G be a vector space. So G just be a vector space. And then we consider the graded vector space C star GG, in which the degree K part are linear maps from wedge n plus 1G to G. And on this graded vector space, we have the Nyhaus-Richardson bracket, which is defined by this formula. So the bracket of P and Q is equal to the composition of P and Q minus the composition of Q and P, where the composition P and Q is defined by this formula. And then it turns out that this graded vector space together with this Nyhaus-Richardson bracket, it is a graded Lie algebra. It is a graded algebra. And actually, there are several ways to understand this Nyhaus-Richardson bracket. For example, you can understand it as the commutator of co-derivations. And you can also understand it as the Schouten bracket of multi-vector fields. And you can also understand this Nyhaus-Richardson bracket as the Poisson bracket on the cotangent bundle T star G. Okay. So there are several ways to understand this Nyhaus-Richardson bracket. And this graded Lie algebra turns out to be the controlling algebra for Lie algebras. Namely, for a linear map from wedge 2G to G, mu. Mu defines a Lie algebra structure on G if and only if the bracket of mu and mu is 0. Namely, mu is a Maurer Cartan element of this graded Lie algebra. Because here is a graded Lie algebra, so there will be no differential. So note this term. Just the bracket of mu is 0. Yeah. Now I will show you that as soon as we have this controlling algebra, we can
you hear me
start
now?
it.
No.
Yes.
Is there a question? Oh,
Can you hear me?
yeah, I can
Yeah.
hear you.
Yeah.
Hello? Was there a question?
Can anyone hear me? No. No, I guess
Yes.
not.
We can hear you.
Yes, we can hear you.
Oh, not hear us.
And
Is there a question? Well, I suggest you just go on and.
Okay. Yeah. So if you have some questions, you can ask in chat also, and my colleagues will answer the question. Yeah. And now I want to show you that as soon as we have this controlling algebra, we can study deformations, cohomologies, and homotopy of the algebras. Okay, so we define d mu by this formula.
Hello. Test.
The inner.
Test.
So are there questions?
Test.
Okay, maybe I go on.
Test. Test. Test.
yeah, so someone's equipment doesn't work correctly, I guess.
Yeah,
so
maybe.
Nikita, is it you? Yeah, I'll write him an email.
Can you hear me now?
Yes, we do hear you.
Oh,
all
perfect.
the time.
Okay, finally. Gee.
Yeah, actually, we did hear you all the time. So should we continue to talk?
Right. I never use Blackboard Collaborate, so I wasn't really familiar with the settings. Yeah. So it took me a while to.
Okay. Yeah, but let's continue the talk.
Okay. So then we can define d mu by this formula, which is the inner derivation by mu. Yeah, since the bracket of mu and mu is 0, so it follows that d mu square is 0.
Perhaps not.
And by the Jacobi identity, d mu is a graded derivation. Then C star GG together with this Nyhaus-Richardson bracket and d mu is a differential graded Lie algebra. And this differential graded Lie algebra will control deformations of the Lie algebra G mu. So more precisely, so let G mu be a Lie algebra and mu prime a linear map from wedge 2G to G. Then mu plus mu prime is a Lie algebra if and only if mu prime is a markdown element of this differential graded Lie algebra. Okay. And then we can use the controlling algebra to study the cohomologies of the algebras. Okay. So it is well known that the Chevalier-Allenberg co-boundary operator DCE, yeah, for the algebra G is given by the following formula. So this is the Chevalier-Allenberg co-boundary operator, and then about the relation between DCE and the controlling algebra, we have the following formula. So DCEF is equal to the bracket of mu and f up to a sign. Okay, so this means that if we do not know the formula of DCE in advance, we can take this as the definition of DCE. Yeah, then we will obtain a cohomology theory. Okay. And finally, we can use the controlling algebra to study homotopy Lie algebras, namely L infinity algebras. So now we replace a vector space V by a graded vector space. So let V be a graded vector space, and we denote by this one to be the space of degree n linear maps from the graded vector space symmetry V to the graded vector space V. And then we denote this space by CNVV. And we consider the graded vector space C star VV, which is the direct sum of CNVV. So then on this graded vector space, we have the graded version of the Nyhaus-Richardson bracket, which is again a graded Lie algebra. And then we can take the following, maybe we can take it as a theorem or we can take it as a definition. So the markdown elements, which is the sum of Lk of this graded Lie algebra, are the L infinity algebra structures on V. Yeah. So we can use this as the definition of L infinity algebra structures. Okay. Here I gave the controlling algebra.
Sorry, I got a question. So is it more or less some version of Chevalier-Allenberg cohomology?
Here is the Chevalier-Allenberg cohomology.
But then in an infinity case, that's some kind of generalization. Is it right?
No, I will not define the cohomology for the L infinity algebras, but I will use the controlling algebra to define what is an L infinity algebra.
Okay.
Here the cohomology is still the classical case.
Okay.
Yeah. Even though we can do that, yeah, it's true. Okay. So here I would like to mention the controlling algebras for other algebras. So in general, they are all graded Lie algebras. So for example, the graded Lie algebra structure for associative algebras is given by the Gerst-Haber bracket on this graded vector space. And the corresponding cohomology is the Hochschild cohomology. And the graded Lie algebra structure for pre-Lie algebras, which is also called left symmetric algebras, is given by the Matsushima-Nyhaus bracket on this graded vector space. Okay, and there are also cohomologies. And furthermore, the controlling algebra for Leibniz algebras for n Lie algebras are all graded Lie algebras. Okay, Okay, since we will see that the controlling algebra for relative Rota-Baxter Lie algebra will be an L-infinity algebra. So here I give the precise definition of an L-infinity algebra. It is a Z-graded vector space G, which is the direct sum of GK, equipped with a collection of linear maps LK from tensor KG to G of degree 1, such that the following two conditions are satisfied. The first one is the graded symmetry condition, and the second one is the generalized Jacobi identity. So there are two conditions, and this is the precise definition of an L-infinity algebra. And we also need the notion of Maurer Cartan elements of an L-infinity algebra, which is due to Geisler. So the set of Maurer Cartan elements of an L-infinity algebra G is a set of those alpha in G0, which is of degree 1, degree 0, satisfying the following Maurer Cartan equation. Yeah, so there are many terms. Okay. Then we can give the following main result, which is the controlling algebra of relative Rota-Baxter Lie algebra. Okay, so let G and V.
Yunhe, can I ask a question?
Yeah.
Yunhe, the previous slides, just continue with Anton's question. If you have the notion of Maurer Cartan elements, next slide. Yeah, next slides. Sorry, the next one. Yeah, sorry, the next one. Yeah, this one. So the sorry.
This one?
Okay. No, right, this one. Yeah. Okay. So the Maurer Cartan elements for the L-infinity algebra, can you, if you have such an element, sorry, can you use this? Can't you use this to define cohomology?
Sure, we can. Yeah. So just now we have this Nyhaus-Richardson bracket, and then you just define this delta, define it to be a sigma Li. You can define delta by this formula. Then it is the co-boundary operator. Yeah.
But this is not the this is not the cohomology of this L-infinity algebra.
It is. It is.
Yeah, it is, but then you must have a Maurer Cartan element to define
because you have first you have an L-infinity algebra, and this means that you have z zeta, you have sigma Li, and then you can define dirt to be taking the bracket of sigma Li. So this will give you the co-boundary operator.
Oh, that is already. So that is Anton's question then.
Yeah.
Okay. Thank you.
Yeah.
Right. Thank you.
Okay. Okay. So now we give the controlling algebra for relative Rota-Baxter Lie algebras. Okay. So let G and V be vector spaces, and we denote by L prime to be the following graded vector space. So notice that there are two parts. So one is composed of linear maps from wedge n plus 1G to G, and the other one consists of linear maps from wedge NG tensor V to V. And we denote by this curly H to be this graded vector space, and the degree n part consists of linear maps from wedge n plus 1V to G. Okay, so we consider these two graded vector space, so they are particularly important in our later study. So yeah, and then we can obtain the following result. So there is an L-infinity algebra structures which we denote by LK on this graded vector space, which is the direct sum of L prime 1 and H, such that its Maurer Cartan elements are exactly relative Rota-Baxter Lie algebra structures on G and V. Here, L prime 1 means that we shift the degree of the graded vector space L prime by 1. Yeah, and then we consider Maurer Cartan elements. So by definition, it is an element. It is elements in degree 0. So we analyze what is element in degree 0. So for n equals to 0, so here it will give you this element. So T is a linear map from V to G. But since we shift L prime by 1, so the degree 0 element in L prime 1 will give you 1 is mu from wedge 2G to G. It lives here, and 1 is rho which is a linear map from G tensor V to V, and it lives here. Okay, so there are 3 elements, which is mu, rho, t, and this theorem tells us that if they are Maurer Cartan elements, then mu is a Lie algebra structure, and rho is a representation of G on V, and t is a relative Rota-Baxter operator. Okay, so now I will not prove this theorem, and I will leave the proof at the end of the talk. But I want to show you immediately that as soon as we have this controlling algebra, we can study deformations, cohomologies, and homotopy of relative Rota-Baxter Lie algebra. Okay. First, we study deformations of relative Rota-Baxter Lie algebras. Okay. Let mu rho t be a relative Rota-Baxter Lie algebra structure, and then we define Lk mu rho t by this twisted formula. So Lk mu rho t of x1 xk is equal to the sum of this one. So here we use mu rho t to twist this formula, and here this Lk plus n is exactly the controlling algebra structures here. Okay. Then, according to Geisler's results, so Lk mu rho t will give us a new L infinity algebra structures on this graded vector space, and we will call this new L infinity algebra the twisted L infinity algebra. Okay, so we obtain the twisted L infinity algebra, and then we can obtain the following theorem. So the triple mu plus mu prime, rho plus rho prime, t plus t prime, where mu prime lives here, rho prime lives here, and t prime lives here. So it is again a relative Rota-Baxter Lie algebra if and only if mu prime plus rho prime plus t prime is a Maurer Cartan element of the above twisted L infinity algebra. Yeah, this means that this twisted L infinity algebra controls deformations of relative Rota-Baxter Lie algebra. Okay, actually, there is
Yunhe, the twisted L infinity algebra is still an L infinity algebra.
Yeah, it is.
It's just twisted by that particular element, but it's still an L infinity algebra.
Yes,
it's not like more general than L infinity algebra.
No, it is still an L infinity algebra. Actually, L infinity algebra is very general. Yeah.
So the original L1, was that equal to 0?
The original
before the twist.
Here,
L1.
In our concrete case, L1 at the beginning L1 is 0, but after the twist, L1 is not 0. Yeah.
Okay. Thank you.
Oh, thank you. So there's a well-known slogan that every reasonable deformation theory is controlled by a differential graded Lie algebra or an L infinity algebra. So you can see our results coincide with this slogan. And under this slogan, there are many related works in Poisson geometry. For example, one can study deformations of pre-simplistic structure, and one can study deformations of direct structure, and all those deformations are controlled by L infinity algebras, actually. Yeah. Now we analyze the twisted L infinity algebra structures. Okay, so recall that H is this graded vector space, and L prime is this graded vector space. So we consider this twisted L infinity algebra structure. We will find that H is actually a subalgebra, which is actually a differential graded Lie algebra. So this H is actually a differential graded Lie algebra. It is a subalgebra of this L infinity algebra, and consequently, L prime 1, on L prime 1, there will be a quotient algebra structures, which is still a differential graded Lie algebra structure. Yeah, but in the middle, this guy, it is an L infinity algebra. Okay, so this twisted L infinity algebra is a strict extension of the DGLA L prime 1 by the DGLA H. Yeah, so we have this short exact sequence of our infinite algebras. And actually, this differential graded Lie algebra H is the one controls deformations of relative Rota-Baxter operator T. And this differential graded Lie algebra is the one controls deformations of Lie algebra structures mu and representations rho, actually. But in the middle, if you want to deform the Lie algebra structure mu and the representation rho and the relative Rota-Baxter T simultaneously, you need an L infinite algebra structure, actually. Yeah. So we have this relation, and then we can study cohomology of relative Rota-Baxter Lie algebras. So let mu rho T be a relative Rota-Baxter Lie algebra, and we define the space of n cochains, which is denoted by Cn mu rho T, by this formula. So there are three components, but recall that actually this part corresponds to this L prime, and this part corresponds to that curly H. And we define the co-boundary operator D directly by this formula. So F is an element here, and theta is an element here by this formula. So here, this L1 mu rho T is the L infinite algebra structure in that twisted L infinite algebra. So it obvious that L1 mu rho T, the composition of L1 mu rho T and L1 mu rho T is 0. So it follows that D square is 0. Therefore, we obtain a cochain complex. So we can give the following definition. So the cohomology of the cochain complex of this cochain complex is called the cohomology of the relative Rota-Baxter Lie algebra. And we denote the nth cohomology groups by this notation. Okay. So now we give the definition of the cohomology of relative Rota-Baxter Lie algebras. As soon as we have this cohomology, we can study infinitesimal deformations or formal deformations or the extendability of order n deformation to order n plus 1 deformations. So here we give a simple example to study infinitesimal deformations. So we consider such kind of infinitesimal deformation, namely mu t equals to mu plus t mu prime, and rho t equals to rho plus t times rho prime, and tt equals to t plus t times t prime. Then we can show that d of mu prime, rho prime, and t prime is 0. This means that mu prime, mu prime, rho prime, t prime is a 2 cocycle. And then consequently, we can show the following theorem. So there is a one-to-one correspondence between equivalence classes of infinitesimal deformations of the relative Rota-Baxter Lie algebra and the second cohomology group. Yeah. Okay. Here we analyze the relations among the cohomologies. So we denote by Cn mu rho to be this space. So recall that actually this corresponds to the L prime, and we denote by Cnt to be this space. Actually, it corresponds to this curly H, and then the co-boundary operator D can be written in the following form. So D of f theta is equal to this formula. Actually, this formula is just compute with what is L1 mu rho T. Yeah. And here, so F is an element in Cn mu rho, and theta is an element in Cnt. And then the components in Cn mu rho is given by this formula, and we define it to be partial of F. So here is the definition of partial, and here we define delta by this formula. Yeah. So we can see that. So delta from Cnt to Cn plus 1t, it is a subcomplex, and this partial from Cn mu rho to Cn plus 1 mu rho, it is a quotient complex, and there are an extra term which is denoted by ht of f, and this ht is from Cn mu rho to Cn plus 1t. Yeah. So HT is defined by this formula. So this guy corresponds to HT. Yeah. So consequently, we obtain a short exact sequence of the cochain complexes. Yeah. So this one is a subcomplex, and this one is a quotient complex. So this is a short exact sequence, and we denote the cohomology of this complex by Hn of t. So this is the cohomology of this complex, and we denote the cohomology of this complex by Hn of mu rho. Yeah. And then this short exact sequence of the cochain complexes will induce a long exact sequence of the corresponding cohomology groups. So we have this long exact sequence. And here, so HNT actually can be taken as the cohomology of the relative Rota-Baxter operator T. And this guy, Hn of mu rho, can be taken as the cohomology of Lie-algebra structures mu and the representation rho. Yeah. And in the middle is the cohomology of relative Rota-Baxter Lie-algebras. So mu rho of T. Yeah. So we have this long exact sequence to describe their relations. Okay. And using this general framework, we can define the cohomology of Rota-Baxter Lie-algebras. So let GT be a Rota-Baxter Lie-algebra, and we define the space of n cochains, which is denoted by Cn RB GT by this formula. So there are two components. And we define the coboundary operator DRB by this formula. So let me give more explanation of this coboundary operator. So this guy is the space of n cochains, and for the space of n plus 1 cochains, it is like this. So home wedge n plus 1 G direct sum of home wedge n G, and DRB is given by 3 elements. Here, it is the classical Stiglitz-Allenberg coboundary operator, and here it is the coboundary operator delta induced by the Rota-Baxter operator T, and more importantly, there will be an extra term, yeah, which we denote by omega. So omega is from home wedge NGG to home wedge NGG. It is defined by this formula. And this formula, you can see it is totally determined by the Rota-Baxter operator T. Yeah, you can totally see that it is determined by the Rota-Baxter operator T. Yeah. And then we can show that the composition of DRB and DRB is 0. So DRB is a coboundary operator. And then we can give the following definition. So let GT be a Rota-Baxter Lie-algebra. The cohomology of this cochain complex is taken to be the cohomology of the Rota-Baxter Lie-algebra GT. So the same as before, we can consider infinitesimal deformations of Rota-Baxter Lie-algebra. For example, we can deform the Lie bracket by this formula plus T times omega, and we can deform the Rota-Baxter operator by this formula, maybe T plus T prime, and then we can show that so DRB of omega T prime is 0. This means that omega T prime is 2 cocycle, and then we can show that infinitesimal deformations are classified by the second cohomology groups. And then also using this general framework, we can define the cohomology of triangular Lie bialgebras. So let GR be a triangular Lie bialgebra, and we define the space of n cochains by this formula. So there are also 2 parts. One part is linear maps from wedge NG to G, and the other part is wedge NG itself. And then we define the coboundary operator DTLB by this formula. So I would like to give more explanation. So here, let me write down the space of n+1 cochains. It contains of home wedge n+1 G and y.
The correspondence between R matrices and Rota-Baxter operator, right? So then you
we need to use this relation and use that general framework to obtain this cohomology.
You sort of use this mirror to put this theory of Rota-Baxter to the side of R matrices. Okay.
So this co-boundary operator DTLB is going by like this. So here it is still the classical Hively-Allenberg co-boundary operator, and here it is dr, where dr from wedge ng to wedge n+1g is given by this formula, just the bracket of r and chi. And moreover, we have an extra term which we denote by capital theta. So theta is from home wedge ngg to wedge n+1g, which is defined by this formula. It is a little small, but you can see that this capital theta is totally determined by this r, actually r sharp. It's totally determined by this r sharp. And then we can show that the composition of DTLB and DTLB is 0. So DTLB is a co-boundary operator. And then we can give the following definition. So let GR be a triangular Lie algebra, and then the cohomology of this co-chain complex is called the cohomology of the triangular Lie algebra. The same as before, we can study infinitesimal deformations or formal deformations of triangular Lie algebra. So for example, we can consider deform the Lie bracket by this formula plus T omega. And we can consider deform this triangular R matrix by this formula, maybe TR prime. So we can show that then DTLB of omega R prime is 0. So infinitesimal deformations of a triangular Lie algebra will be classified by the second cohomology group. Then we can study homotopy relative Rota-Baxter Lie algebras. So let G Lk be an L-infinity algebra and V rho k be a representation of this L-infinity algebra. And then we consider this graded vector space H. So the degree n part consists of linear maps, degree n linear maps from the graded vector space symmetry V to the graded vector space G. And on this graded vector space H, there is an L-infinity algebra structure, Lk, and Lk is defined by this formula. So Lk of A1 and A1 and Ak is equal to this formula. So first, you consider the sum of Lk plus rho k, and then you take brackets of A1, A2, and Ak, and finally you take the projection. So here P is the projection from this big space. So home symmetry, we consider the direct sum of G and V to G and V. And then we consider the projection from this space to this H. And then this will give you an L-infinity algebra structure. Consequently, we can give the following definition. So a degree 0 element T is a homotopy relative Rota-Baxter operator on the L-infinity algebra structure on the L-infinity algebra G with respect to the representation V rho k, if and only if T is a markdown element of this L-infinity algebra. So this means that this L-infinity algebra is the controlling algebra of homotopy relative Rota-Baxter operator. So this is the definition. And here I would like to to say a remark. So Dosenko and his collaborator studied the homotopy of Rota-Baxter operators on associative algebra in this paper, and they noted that so in general, compact formulas are yet to be found. So for Rota-Baxter Lie algebras, we believe that one will encounter a similarly challenging situation. So nevertheless, we use the approach of controlling algebras and their markdown elements to formulate the notion of a homotopy version of a relative Rota-Baxter Lie algebra. So hopefully, our research will provide some useful information for the operatic research of the homotopy of relative Rota-Baxter Lie algebras. Here, I would like to give the explicit formula for a homotopy relative Rota-Baxter operator. So the degree 0 element T, which is the direct sum of Tk, and the Tk is in this space, is a homotopy relative Rota-Baxter operator on an L infinite algebra G with respect to this representation, if and only if the following equalities are satisfied. So you can see this formula is a little complicated, but we can compare it to the classical case. So for a relative Rota-Baxter operator, so in the classical case, for a linear map T from V to G, if it is a relative Rota-Baxter operator, so here at the right-hand side of the equality, it is simply Tu, Tv, then taking the Lie bracket, and at the left-hand side, it is simply T of rho Tuv minus rho Tvu. So this is definition of relative Rota-Baxter operator. So you can see that. So here, because there are different Ln and different Tk, so the formulas becomes complicated. And at the left-hand side, because there are different rho, because in the representations there are different rho, so the formulas like this, Okay, so in the sequel, I would like to give the relation between pre-Lie infinity algebras and homotopy relative Rota-Baxter operators. So the notion of a pre-Lie infinity algebra was introduced by Chartan and Leibniz in this paper, and by definition, a pre-Lie infinity algebra structure on a graded vector space V consists of degree 1 linear maps theta k from the graded vector space symmetry V tensor V to V, such that the sum of theta k is a markdown element of this graded Lie algebra. So recall that at the beginning of the talk, I mentioned that we have the controlling algebra for pre-Lie algebras. And here we just replace a vector space by a graded vector space. We can still obtain a graded Lie algebra, and then its markdown elements will give you the pre-Lie infinity algebra structure. Okay. So I will not write down the explicit formula. Just you can view it as the markdown element. And then, given a pre-Lie infinity algebra G theta k, we can define Lk by this formula. So it is some kind of take summation over some permutations. Then GLK is an L infinity algebra denoted by GC, which is called the sub-adjacent L infinity algebra. And furthermore, we define capital Lk from symmetry k-1g to GLG by this formula. Then we obtain the following result. So GLK is a representation of the sub-adjacent L infinity algebra GC. Moreover, the identity map is a strict homotopy relative Rota-Baxter operator on the L infinity algebra GC with respect to the representation GLK. So roughly speaking, a pre-Lie infinity algebra will give you a new L infinity algebra together with a representation on itself. And furthermore, the identity map will be a homotopy relative Rota-Baxter operator. Okay. So, and conversely, from a homotopy relative Rota-Baxter operator, we can also obtain a pre-Lie infinity algebra. So let T be a strict homotopy relative Rota-Baxter operator on an L infinity algebra GLK with respect to the representation V rho K. Then on V, there is a pre-Lie infinity algebra structures. Here, set K are linear maps defined by this formula. So it is a little complicated, but we can compare it to the classical case. So in the classical case, as soon as you have a relative Rota-Baxter operator T from V to G, then on V, you can define a new multiplication U times V. You can define it to be rho of TUV, yeah, for all UV in V. Then this will give you a pre-Lie algebra structure. So this formula is just the infinite version, yeah. Okay. So maybe I talk a little bit about the R infinity matrix. So the notion of an R infinity matrix was introduced by A. Vernoff and his collaborators in this paper. And in the classical case, a triangular R matrix gives us a relative Rota-Baxter operator with respect to the co-adjoint representation. And here, as expected, so an R infinity matrix gives rise to a homotopy relative Rota-Baxter operator with respect to the co-adjoint representation. Okay, so maybe now I have maybe 8 minutes, and I will give the proof of the main theorem, give the proof of the construction of the controlling algebra structures. So what we need is the T-Vernoff's derived bracket. So first, I gave the definition of V structures. So here V V stands for T-Vernoff. So a V structure consists of a quadruple where L is a graded Lie algebra and H is a abelian graded Lie subalgebra of L, and P from L to L is a projection whose image is H and whose kernel is a graded Lie subalgebra of L, and the delta is an element in kernel P of degree 1, such that the bracket of delta and delta is 0. So delta is just a special markdown element. Yeah, so this is the definition of a V structure, and the T-Vernoff showed that given a V structure, one can obtain an L infinity algebra structures. Okay, so let L H P delta be a V structure, and then we consider this graded vector space, which is the direct sum of L1 and H. There is an L infinity algebra structure defined as follows. So L1 XA equals to this. So the component in L1 is given by this formula, and the components in H is given by the projection of this formula. And L2 XY exactly the original graded Lie bracket, and you define LK by this derived bracket. So you, for example, LK x A1, a k minus 1, you take the bracket of x and A1 and A2 and AK minus 1. After this bracket, you take the projection to H. So this is definition of LK, and this will give you an L infinity algebra structures. And this is a very powerful approach to construct explicit L infinity algebra structure. But in general, this L infinity algebra structure is too big. We will need a smaller one. So let L prime be a graded Lie subalgebra of L such that the bracket of delta and L prime contains in L prime. Then on the direct sum of L prime 1 and H, there is an L infinity subalgebra structure of the above L infinity algebra. Yeah, we will obtain a smaller L infinity algebra structure, and this one exactly what we wanted. Okay. Now let G and V be two vector spaces, and we have a V structure as follows. So the graded Lie algebra is given by this guy. So we consider the direct sum of G and V, and then the associated graded vector space. There is a Nyhaus-Richardson bracket, which is a graded Lie bracket. And we consider the abelian graded Lie subalgebra H by this guy. Actually, we have used this curly H several times, so it is the same as before. And we define P from L to L, just the projection onto the subspace H. And we simply take third to be 0. So this is a V structure. It is straightforward to verify this fact. And consequently, according to Verneuil's result, we obtain an L infinity algebra structures on the direct sum of L1 and H. And here, because delta is 0, so the L infinity algebra structures becomes easier. So you can see here we use delta, but if delta is 0, so the formula is easier. So it looks like this. Okay, and then we are ready to formulate our main theorem. So the L prime, which is also used for several times, and it is a subalgebra of L. So it is easy to verify this fact. So it is a subalgebra of L. Then on the direct sum of L prime 1 and H, there is an L infinity algebra structure. And this L infinity algebra structure is much more easier than before. There are no L1. Yeah, you can see here L1 needs the projection, but because here we take the subalgebra L prime, so the projection is 0. So the L infinity algebra structures is easier than before. And moreover, let mu be a linear map from Y to G to G, and rho be a linear map from G tensor V to V, and T a linear map from V to G. So mu rho T is a relative Rota-Baxter Lie algebra if and only if mu plus rho plus T is a Markov element of this L infinity algebra. So this means that this L infinity algebra is a controlling algebra of relative Rota-Baxter Lie algebras. Okay. So we roughly give the proof of this theorem. So we just need to compute the Markov equation. So after the straightforward computation, we found that there are only 2 terms left. So if mu rho T satisfies the Markov equation, this means that the bracket of mu plus rho and mu plus rho is 0. Furthermore, we have this equality. And by the first equality, we obtain that mu is a Lie algebra and V is its representation. And by the second equality, we can obtain that T is a relative Rota-Baxter operator on G with respect to this representation. Okay, so that's all what I want to talk. And here are references. Thanks for your attention.
Thank you.
Thank you very much. Thank you very much. Are there some questions? Okay. So probably I have a question about this relation with our matrices. So this Rota-Baxter operator, so if you have a R matrix, then you can give yourself a Rota-Baxter operator, right? And And is that also the other round? Like if you have a Rota-Baxter operator on I guess you have to have the actual representation.
Yeah, but yeah, for the other side, so if you have R in value to G, then we consider R sharp from G star to G. It is a relative Rota-Baxter operator on G with respect to the co-adjoint representation. But conversely, if you have an arbitrary relative Rota-Baxter operator T from V to G, and then it can give rise to certain triangular R matrix, but you need to consider some bigger algebra, namely, so T is from V to G, so you can view T as an element in V star tensor G. So then you need to consider this semi-direct product Lie algebra, G and V star. So you use rho star. So you have a semi-direct product Lie algebra, and this T, you can see T is a two tensor for this Lie algebra, right? So T is two tensor for this Lie algebra because it's V star tensor G. And then this T will give you a triangular R matrix. Actually, if you need to take the skew symmetry, the skew symmetrization, maybe T plus sigma T. So then it will be skew symmetric. Then it is a triangular R matrix in this Lie algebra. Yeah. You need to consider a bigger Lie algebra. Yeah.
Create a bigger. But, and this construction, the going back, this construction is also stable under homotopy. You can add homotopy on both sides where you have R matrix after homotopy and also this Rota-Baxter.
Yes, yes. As I said, so we can consider the so-called R infinity matrix. Yeah, and then it will give rise to homotopy relative Rota-Baxter operator. Yeah, and conversely, yeah, I think it's true. Yeah, conversely, if you are given a homotopy relative Rota-Baxter Lie algebra, and you can also still consider maybe this semi-direct product, because for the infinity algebra, this fact still holds. Yeah. Yeah, I think. Yes.
Okay. So I see Dima has a question.
Hi. Okay, so I just want to mention that when you said pre-Lie, okay, it was not by Hamilton and Leibniz. It's already introduced by Jackson Harbour in 1963 in his Annals of Mathematics.
Okay.
Yes, but it used by other people in later years under different name, like right symmetric and Weinberg algebra and so on. So in this paper, Hamilton and Leibniz kind of revisited Jackson Harbour's notion and suggest that we use this name.
Okay.
We continue to use this name, pre-Lie, yeah. But this name itself was already in Jackson Harbour's paper.
Okay. Yes. Thank you very much. Yeah. Thank you very much for this history. Yeah. Okay.
Yeah.
So that was not Dima. So maybe Dima, do you want to ask your question now?
Yes, please, if I may. Let's see. Right. So yeah, I had a question. First of all, whether your L-infinity algebra has only finitely many non-zero brackets or infinitely many of them.
Yeah, that's a very good question, because if one consider the markdown equation, you need to consider the convergence, right? Yeah. So yeah, there are some technical tools to deal with problem. Yeah. But for our concrete case, there's no problem, because at the end of the talk, you can see if we compute the markdown equation, yeah, there are only two terms actually.
Yes, I saw that, because, well, I mean, from the very beginning, your structure consists of these three components satisfying finitely many algebraic equations. Okay, I didn't quite catch. I mean, it went by a bit fast, like the whole formula for what the space is like. But is it true that all elements of degree 0 are of this form? Do all of them only have those three components?
Yes. Let me show you. Okay. Let me see where it is. This is a cohomology. Maybe
yeah.
So here you can see. So H, where the H? So H is this space is home wedge n plus 1 way to G. So by definition, a linear map from wedge n plus 1 way to G, it is of degree n. Yeah, so here, if we consider degree 0 map in H, it will correspond to T from V to G. So it is a degree 0 guy. And for this L prime, because we shift it by 1, you see, we shift L prime by 1. So the degree 0 elements in L prime will
okay, that's the other two.
Yeah, the other two. Mu is from wedge to G, and the rho is in home G tensor V to V. Yeah, because originally mu is of degree 1, but because we shift L prime by 1, so mu is of degree 0. Yeah. So these are all degree 0 elements. Yeah, mu, rho, T.
I see. So is this yes? So also, what is the context for this? For the what deformations is this controlling algebra controlling? Because you know that there are different answers depending on whether you want to deform only part of the structure or the whole thing. So is this just for deforming T or everything?
There are okay. So the controlling algebra I said in this talk, it just means that control this algebra structure, namely the markdown elements. The markdown elements are relative to the Rota-Baxter Lie algebra. So this is the controlling algebra mean in this talk. But as you said, in some other cases, maybe I would say the controlling algebra of deformations, for example, and here we control. You ask, we control what kind of deformation? We control simultaneous deformation. We deform both mu and rho and T. Yeah.
Okay.
We consider simultaneous deformation. Actually, if you only consider T, if you only deform T, a differential graded Lie algebra is enough. You do not need an L infinite algebra structure. But if you want to deform them simultaneously, you need this L infinite algebra structure. Yeah.
Okay. And may I ask another question, or might?
Sure.
Yes. So, what is what is the operatic interpretation of all of that? In particular, I'm curious about that table of algebras of 9 algebras, because like you're applying these operators, in turning one kind of algebras to another kind of algebras. But is it clear to you what what's happening on the level of like what that's doing to the operands?
Yeah, but here maybe I cannot say more, but I can tell you that for Rota-Baxter algebras, it is not a quadratic operator because there is a unary operation T from V to G. So it is not a quadratic operator. So the usual approach to study homotopy of algebras using operator approach does not work. And Dosenko and his collaborator try to study the homotopy of Rota-Baxter operators using the operator approach, but it is very difficult to find the explicit formula. So they gave some calculations in lower terms, but in general the formulas are not yet to be found. So as I said, now people do not know how to study homotopy of relative Rota-Baxter algebras using the operatic approach. And here we use this controlling algebra and their Morgan elements to formulate the notion of homotopy relative Rota-Baxter algebra.
Maybe Dima want to ask this table, like what is Rota-Baxter operator mean for this splitting of operas?
And so Rota-Baxter operators actually here there are 9 algebras, maybe here actually. So here this splitting can be lifted to the level of operas. For Rota-Baxter operators, if you consider the operator of the algebras, and then you can consider the splitting, and you will obtain the operator of pre-Lie-algebras. And actually Rota-Baxter operators play such a role.
Right. So the last remark that this the Voronov construction is the homotopy fiber of the inclusion of that abelian subalgebra.
Exactly. This is the intrinsic of the higher derived bracket. You are totally right.
Okay. Thank you very much.
Thank you. Nice to see you online, Demi. Yeah.
Are there more questions? Okay. So if no more questions, let's thank the speaker again.
Okay. Thank you very much for the listening.
See you next time.
Okay. See you. Bye.
See you next week.
Bye, everybody.
Bye.
Goodbye.
Bye. I just see the
Bye. Bye. Thank you.
Professor Cosmo Schwarzbach. Nice to see you online. Bye.
Yes, very interesting. I enjoyed it. I had a question, but too difficult to ask.
Right. Actually, at the beginning of this research, we only consider deformation of the operator. Actually, we use Yau's derived bracket. But later, when we consider simultaneous deformation, we need to use Voronov's higher derived bracket. But at the beginning, we use Yau's derived bracket. Actually,
Yes, I realize, but things go very fast.
Okay.
To higher levels. But no, it was very interesting. I think I followed what you were saying, but I have to read your papers, of course. And sometimes I do, but not very often.
Thank you.
Okay, thanks for the talk.
Thank you. Bye. Take care.
Bye.